So the presentation I'm going to hold is not identical to the implementation I had, and that's due to security reasons, and I was not exactly. But it shows how we modeled and solved the problem in general. So all the presented data, the data I'm going to present, numbers and charts, they're real and they're from production. And that's important. So I'm from Telenor, Norway, which is a telco, and we're part of the Telenor group, which is worldwide, but with headquarters in Norway. And the mobile revenues for Telenor last year were $2 billion US. So there's quite a lot of cash going through the system. And I was the lead developer and architect of the new Neo4j solution. And it has been a project that was ongoing for a couple of years and is now in the full production. So telcos, they might not be that interesting as other areas, but they're really important. And I mean, everyone here probably have a mobile phone, right? So everyone needs the telcos. And the good part is, since everyone needs it, it's a very good market for us. And it generates a lot of money and it generates a lot of data. And that's the fun part with working in the telco, because there's a lot of money and a lot of data. You actually get a lot of problems that are trying to solve if you're like a technical guy like me. Okay, so the thing I'm going to talk about today is it's rather simple. It's a simple use case, but it gives a really high value for us. So everyone who has like customers and products, they should relate to this. This is not unique for a telco, but this is how we have used it to solve a problem that we have. Okay, so resource authorization, that's a part of data security, and it's extremely important for us. So imagine if you don't handle this correctly, what happens if someone else might get your number and you want that to be a secret number? Or if they're able to modify your subscription or even delete it? Or what if they actually manage to send or receive text messages that you're supposed to have? That's really bad. So it's very critical for us that we have a solution that's working extremely well. So this is a picture of the middleware services that are using Neo4j today. We have a monolithic kind of middleware. We have a lot of different channels. So one channel is like a group of clients, right? So it can be an app, or it can be like a web solution for enterprise customers, or be a web solution for consumer customers. And we have like a lot of different channels. And we have in the order of 20,000 orders a day coming into the system. Everything goes through this monolithic system, middleware. So, since all the data that is requested through the middleware tier goes then to Neo4j to check if we're allowed to return that data to the asking client. And the middleware tier solves requests that are like customer or product based, like more kind of CRM, but it also supports more kind of operational services, meaning that if you log on to like Wi-Fi in hotels in Norway, and they have a deal with Telenor providing the Wi-Fi, and our system is down or Neo4j doesn't respond correctly, then you don't get access to that Wi-Fi. Or if you try to send an SMS through your computer and not your telephone, you also have to check that you have a valid subscription. And if that fails again, you're not able to do like basic operations. That's really bad. So with using Neo4j that we do, it's really important that it's stable, and it really works well. If not, we have a really big problem, because we're backing all of our data and return from the middleware on this solution. Okay, so the problem. The previous solution we had for our large corporate customers, it used about 20 minutes to calculate all the resources that user had access to. Like if you had an administrator, you could administrate that company and all the subscriptions. And that might be several hundred thousand resources he had to calculate. And so I was going to show how that was done. And also, in order to do this calculation, which was graph-based, we had like a stored procedure or a couple that was like 1,500 lines of SQL code. Because SQL is not designed to do traversal. And doing this combined with the structure that we had that was designed for also other purposes, it became really messy. And I remember I used like weeks trying to understand how it worked, and I really didn't get it. So, and there were several people trying to understand. It was really hard to understand business rules. So, since it took so much time to do this operation, we solved that by doing like a daily cache. So, each night we would calculate for our large customers all the data they could access, and then we would store that in a cache. Right? Great idea. Unless that data changed during the day, or you modified the kind of access the user had, or you created a new user, then you had to do it again. So it wasn't that great an idea. And also, the problem was that with growth, with the number of administrators and users growing and portfolios, this solution didn't scale. So, how did we get the idea about using a graph database? It was really easy because we had this meeting, and one of the people who needed the old solution, it was like, okay, this is how it works. So we had like a whiteboard, took out the pen, and started drawing. Okay, so we have a user, and he has access to a company, if it's an administrator. Okay, and this company may consist of other companies, right? Which again may consist of other companies. So we have some large structures. And they have, of course, departments. Okay? They have to be modeled. Because when you have like different departments, you might want to have billing for one department separately and another department and so on. And below there again you have subscriptions, like all the phones and stuff. They need a subscription. So at the bottom you have all the devices that are using the subscription. So you can have one subscription, and you can have your cell phone, your tablet, everything connected to that subscription. The point was that we really fast saw that when we drew it on the whiteboard, is that in order to calculate the data you need to access, you're actually doing traversal. And then that was the idea, like, okay, this is a traversal. This is when you're supposed to use a graph database, right? And that's how we know that it's the correct technology. When you do a traversal, okay, then it's the graph database. Okay, so the solution we did was then we had a tailored read model. So instead of just trying to change the master data, we do it like a replication of the data that we need, and we make that data model within the graph database as efficient as possible. So the first thing that we did was first try to find the kind of questions we wanted to have an answer for. And when we did that, we found the optimal model to use in the graph database, because that wasn't actually similar to the one we have in the relational database. So on a high-level architecture, you can see we have all the clients which uses the middleware. And because we also have feeds into the relational database from scripts and so on, other systems, we have a replication from the database and a message queue, which is then read by the Neo4j instance or server instance and stored into Neo4j. So that's a high-level architecture. And then the classic the middleware will then go and do a check access for the resource it tries to retrieve from the Neo4j resource authorization solution. Okay, so, but it's more than just having to traverse the graph simply. So, because we have different needs. And then we have the layer with conditional rules. So, conditional rules saying that not all users are allowed to access all data in the structure. And that's why we model on the axis we have model properties. So, we have two properties. I'll show you use cases. It's basically you can have access to content and you can have access to the subsidiaries. So, if you have access to subsidiaries, then of course you're allowed to follow the parent company relationship. If not, you're not allowed to follow that. And if you have access to content, then you also may see the departments below the company level and subscriptions. So, two rules we need to take into account here. So, this is the model, why we need it. Let's say you have this structure. Then you have a super user. He wants to see everything. Okay? That's fine. So then you have two flags saying you have access to both content and subsidiaries. But then you have a special case where you only have access to the top level node, the company on top. So I don't know what you have in the US of that kind of companies, but you have like umbrella company on top. And then you have other companies below. But the top company is not like, it's an organization kind, so we're not allowed to go into the details of the companies below. So it's like just a structure to give you like benefits. So all the companies registered in this organization, they get like a reduction in the price for a subscription. So that's the second case. And the third case is that you have an administrator who don't have access to the entire structure, but just part of the structure. So then it would not be like this. So that's why we need these different rules. Okay, so based on the information, like you have the structure that you traverse. These are the allowed relationships to follow and the directions. And in addition, you have the rules that you have to apply. Then you have like algorithm. This is the algorithm we want to implement in your project. Okay, so what's the value of doing this? Well, first is performance. Okay, we went from minutes to seconds, and in some use cases, milliseconds. So I'll get back to it. It's driven by performance, no doubt about it. But the second thing that's important is simplicity, because SQL is not designed to do traversal. So it's really hard to model and it's really hard to read. And that was one of the main problems, that nobody in the organization understood the rules that was implemented. Nobody. After rewriting it, it's really simple to understand. That's another benefit. It's not just about performance, it's also about simplicity, of understanding what's going on. And the third thing for us was scalability, and that comes with the performance part. Of course, when you don't have, of course, we didn't have good enough performance. With growth, it didn't scale. So now that we have really kick-ass performance, it also scales. And that was the driver for the business case. It was a really good business case, because if we didn't do this together with something else, but it was like half of the performance stuff we did, and scalability stuff, then we would be able to onboard more corporate customers. And that business case alone paid for this project, which was pretty huge. Also, what we did was, the previous solution was implemented as stored procedures in a relational database. Okay? And having too much stuff into a relational database, like modeling everything, that's a problem in trying to separate it out. So we actually used a lot of time just to manage to take it out. We had to rewrite a lot of the use cases accessing the relational database, because we couldn't do like the joint part anymore, because everything was joined in the relational database. So we have taken it out as a separate service. That was quite a bit of work. But the nice thing is now that we have done this like once, separated out functionality in a separate service. So the next time, if there's a next time that we want to change the implementation from Neo2j to something else, or not a relational database, graph database at all, then it's much simpler to do the next time, because now it's a standalone service, it's not an integrated part of a relational database. Okay, so just to say something about the complexity about the authorization algorithm here. So, we haven't seen this yet, but it's not a collection of isolated trees. That would be much simpler, right? You can think of the different customers and thinking they are like separate trees. That's not entirely true, and I'll get into more details later. Actually, a couple. And not all the users, as I told you, have equal access. It's not like a fixed schema, form, or size for all the customers. I mean, there are all kinds of different structures. And it's updated continuously. So it's not something you just pick up, analyze, and then use. So this together makes it like a huge graph, which is live. And it's, well, it's complex. It's not simple doing this kind of resource authorization. But this tool makes it much simpler. So I'm going to tell a bit how we started using Neo2j, because I think it was a good way of starting to actually use any kind of technology that worked very well with Neo2j. So basically the approach was we had the idea that the graph database would be a good solution. So we did basically research on the internet, trying to find out which databases are in use, what's popular, what seems to be a good choice, and Neo2j seemed to be a good candidate. So, okay, we picked the candidate, and we downloaded it and started prototyping, okay? Just to see, does it work, can we model, okay? And it seemed to be a good match to our requirements. So, when we decided to go further, we quickly contacted Neo2j, and we set up a workshop. Of course, it's new technology, and we wanted to be sure that we didn't really model the stuff wrong. It's quite different from working with relational databases. So we pretty quick gained confidence with it, and also had a design Q&A by Neo2j to help us. And then we actually didn't use them for maybe a year, something like that, doing like everything ourselves, until just before we went into production. Okay, and at that time we again had like meetings with Neo2j and showed them what we had done. Does this seem like a good way of doing it? Have we done something wrong? And also we had some issues with performance, so we had help sorting them out. That's really great. So we didn't do like a wide search and tried many different things. We just went for one thing that we believed in, and it has been working pretty well. So, lessons learned. And I mean, that was also said from others, is that when you have a problem, it's about finding the right match of technology or solution. So it's not about using relational databases for everything. It's not about using graph databases for everything. It's about using graph databases where they work best, right? And relational databases where they work best. So also it's an entirely other way of thinking. So you need to build competence. It's not, if you have like DBAs or database people, they are probably the last people you want to work with this, because they're so, but you need to build the competence. It's not, it might seem trivial when it's explained, but when you go into the details, there's a lot of thinking you need to do, how it actually works. And also, we might be like early adapters also, but we used a Java API, and profiling was really important. And also because we had logic that I'll show later, that ran like each time you do a traversal, like a jump from node, then you execute some logic. And if you don't write that logic well, and you do that like thousands or millions of times, then you really see it in the performance. So performance tuning in this case is really important. And And also, don't put everything into the graph. It's really easy just to start putting everything, but then you'll also see that it's going to get slow. So model like one problem using the graph database. If you have another problem, create a separate graph. Don't put everything into that one graph. Then you're starting to do like how we did it with the relational database. Everything into the relational database. That's not a good idea. And also, you actually need to know how the traversal works, or at least it's a good idea. So there's a library, shortest path, which comes with Neo4j. You can use out of the box. And we use that in one part of our code. And we went from version 1.7 to 1.8, and it changed implementation. And suddenly our performance dropped. It was really bad. And that's because they had done, it's what the algorithm previously just went like in one direction, doing the shortest path, and then went to be bi-directional. That's okay, like in general that might be a good idea, but in our use case, that was a bad idea, because we have a tree structure. And for the traversal we're doing, it's actually a benefit if you just go from the one direction and not both. Because it's expanding like the one direction and it's going into like fork in the other direction. So you actually need to know pretty well how the algorithm works and how the traversals work. And the last part is, I think it's smart to benchmark the solution just to find out if you have any speed problems, where are the problems, what is it related to. So we did like, I took the code and I removed all the logic, like we implemented. I just like walked traversal just to see what kind of performance do you get then, because you don't have like, it's hard to say what is acceptable performance, what is good performance, where is the bottleneck. So benchmarking on your hardware just to see what kind of performance you get is a really good idea. Okay, so Neo4j or graph databases wasn't the only option. And another option that we looked into was doing relational databases with having like an in-memory solution. And the DBA pushed for that, of course. He said we should like buy this in-memory solution. It's really great, really good performance. And okay, that might not be a bad idea. So the first option was using the database as is, okay. But the problem is it's like shared with all the other use cases, so we'll have performance just because of that. It's also in a structure that's not optimized for your problem, okay. And you have performance hits due to that. And you still have the complexity with the SQL, which is really complex. And the other option was, okay, what if we take fresh database, replicate the data into that, just the data we need, to make the structure ideal for the query we're going to do. So I read a couple of articles about that during the time it chose to go for graph database in Neo4j. And some of the articles, they claim that I had similar performance to a graph database doing it in memory. Okay, and I mean, great, then you get the performance. And the technology is familiar, so you can use your existing DBA, right? That's good. But again, you still have the complexity. So if complexity is part of the problem, then it's still not a good solution. So, but we decided to go for the graph database, obviously, since I'm here. And we haven't regretted that. But just to say that it might be an option doing like relational database if performance is the only requirement. So, okay, now we're starting to get into the details. So these are the different structures that we have. So we took like, of course we have 5 different structures. The first one, company X, is like a normal company structure. Company Y is where you have an umbrella organization on top. And company Z is end-to-end market. So where we have typically you put SIM cards into devices, right? Into your fridge or into your car or into alarms, whatever. So they get like different shape. So we wanted to try different kind of structure to see how it goes in performance. So this is in production, you don't actually log at user or customer level. So the numbers you're seeing here are actually on top, are retrieved from the test environment. But in order to have something that is really from production, for a single customer, I did like sampling just before I came. So, and you have that at the bottom there. So, to calculate all the subscriptions you have access to for one of our largest customers, so he has access, the user will have access to 215,000 subscriptions. It takes 2.4 seconds to calculate that. And you see for other structures similar performance. Okay, so it takes seconds to calculate all the resources. Now the interesting thing is, what if I just want to see if I have access, taking an entire database, in the entire graph, taking a user, taking a single resource, check if I have access to that, of all the data. That takes 1 millisecond, all the different cases, 1 millisecond. And that's fast. And I'll get into the details in the next section, why it's so fast, because we needed to do something clever there. Okay, so how does this compare with what we had? Okay, that's important. So the previous solution, we did different samples in production. So worst case, when you access and it's not cached because we don't have in-memory database, we have a lot of data, so everything is not in memory. So for company Y, which had a reverse result, it took 22 minutes to calculate all the resources it had access to. Okay, so when you log on, it takes 22 minutes just to log on and calculate which resources you have access to, and 12 minutes and 3 minutes for company Z. So it was minutes. Okay. And that's not acceptable. And if it was cached in memory, it went faster. But the problem is, it's just staying in the cache in the database for maybe a minute, and it's thrown out because all the data going through the database. So, but it says something about if it was in memory, how fast would it go? Not optimized, obviously. So when you do this with a graph solution, it takes 2 seconds to calculate everything. Again, if you just want to check access to a single resource, it takes 1 millisecond. And also, we have been running this for in full production for half a year, and we have in partial production for a year and a half. So we have, since we put it into production, we haven't had any operational problems at all. So next part, I'm going to go into more details. So we'll see. Of course, there's always somebody who likes more details. Depends on what kind of kid you are, obviously. So this is for the people who knows more about the technology, maybe, and has worked a bit with it. So just to say something about the size, we have 27 million nodes. So it's not a huge amount compared to a lot of cases you have seen, but it's still quite a lot. So 27 million in Norway, that's pretty much. So, and everything is in heap. Performance is the most important part here. So we have 20 gigabyte heap, and 15 gigabyte of that is used when we have just loaded everything into the database. We're running the CMS garbage collector. We haven't seen any full garbage collection in production during the last month, which I was able to scan in detail. Of course, that's about how far we have detailed logs. So, and one reason for that, of course, everyone who knows how the garbage collector works knows that we will eventually have full garbage collection. But we have a nightly restarts of the servers just to have full sync of the database. We do like synchronization during the day, but in case there's some problems with the messages for whatever reason, we have a nightly sync as of now, also in addition. So, for traffic, we have about 1,000 requests a minute, so it's not huge, but it's still quite well used. And we also have like 4K updates real time from the relational database as the data is updated during the day. Okay, so this is from the production, just output. So, interested. This is to say something about the stability of the system. So if you look on the top, these are like percentiles. So the red one would be like actually maximum of what we have seen, maximum response time for has access to a resource. And then you have the 99 percentile and you have the 50 percentile. So the 50 percentile is like at 4 milliseconds, the 99 percentile is, no, those yeah. So, no, the 99 is for 4 seconds. So, and you see like the maximum here is, it's still like below 1 second in response time. So if you see the middle one chart, you'll see like almost all responses, queries are responded within like 4 milliseconds. And the last one, we did like exponential display, just to see easier how many it takes like a lot of time. And you'll see that it's for more than 1 second, it's like less than 20 queries like during the last month out of maybe more than 10 million queries. That took more than 1 second. So it's not that we have, I mean, due to the heap being 20 gigabytes, and you know that you will have garbage collection. So the worst performance we're seeing, right, is the last month is something between 2 and 4 seconds. That's the worst response time we have, right? And of the 10 millions, it's just like less than 20. That was really okay, bad, it's not even a second. And compared to what we have, that's really great. Also, if you look at all the queries, we'll see that the worst response time we have is actually nothing worse than 8 seconds. That's the worst response time we have when you query all the different kind of queries, even when you ask to retrieve all. So if it might have been high load and garbage collection, still it's nothing worse than 8 seconds. And it's just like, I mean, from 4 to 8, it's less than 5 queries during the last month that have that kind of response time. And the last one is the garbage collector. You can see it's how it's working. So it's around from 15 and a bit up. But you also see the red ones. That's the pause times that are important. And you see that pause times, the worst pause times are just like about 1 second. That's the worst pause time we have with the 20 gigabyte heap. Okay, so now a bit more about the implementation details. Okay, I need to speed up here, I see. We're using the Java API. And this is basically how it works if you use Java API. You have like a traversal description, and into the traversal description, you put the evaluator and expander, okay? And then you do the traversal, which returns nodes. And in this case, you have a start node. Start here, start at the user, see what gets access. So, the evaluator is basically, am I going to return a node or not? That's what we're doing. So if you like the node, maybe it's the node type. If it's like subscription, want to retrieve all subscriptions, great. You say, implementation says just, if it's a node of type subscription, then return it. And the other part is the expander. So the split is like, the evaluator just says include or exclude. An expander is where the business logic resides. So this is the single most important class in the solution, because here is all the business logic. Okay. The other, this one, the evaluator is just used. It's different for each use case. But the expander is like one class used for all queries. And that's important because of security reasons. We don't want to have like different implementations of the traversal was allowed, because it's just one definition of what's allowed, how acceptable traversal is done, using the relationships you're allowed to traverse and the rules that apply to the access. So do you have access to content? Do you have access to the subsidiaries? This is the one class that masters that traversal. So basically, you have like expand, like when you're in a node, you expand. And if it's an access relationship, then you check for properties. Does it have the access to subsidiaries, the access to content properties? So we pick that up from the relationship. And we actually also find the kind of expander we want them, because if you have access to everything, and then you have this expander, you're going to use them. And we set the expander because you have like state flag input on the traversal. So we put the right expander, set it as a state, and then you use that throughout the traversal of the graph. So the get expander basically, based on the parameters, create is like build the correct expander. So if you have access to subscriptions, add these relationships. If you also have access to content, add these relationships. So now you have a perfect description of the allowed traversal. So again, the thing about how you got like 1 millisecond response time for if you have access, that was a trick. Of course, we know that if you do fan out traversal on top, then basically, if you're trying to find like one subscription, if you're unlucky, it's the last node you're going to traverse. Okay? Because you don't know where the subscription resides, so you just try all different solutions. So instead, because we know this tree structure, we said, but what if we start at the subscription? Okay, so then you do the traversal first, upwards. Because it doesn't fan out when you climb upwards. And then when we find the use node, then we go down again. So the upwards traversal will identify all paths possible up to the user. And then we do the down traversal actually, where we apply the logic. Because one of the first things we do in the traversal expander is to check like access. Do you have access to content? Do you have access to subsidiaries? And then we have to start on top. So, but again, from the performance, this was a really big difference then, because I mean, it might take a couple of seconds just to do it. In start, when we first implemented, it took a couple of seconds in work case. And after we did it, it always took like 1 minute. So that's like, and again, you need to know how it works. Okay, and I'll just shortly tell you, okay, there are also other problems that we saw. So one problem is, what if you start to allow relationships back up in the structure again? Of course we had that. And it's also solvable, but again, you need to know how traversal works, how graph works, because this is a problem you might get that. It's not just about traversing and everything works fine like you go down in the graph. What if you go up again? Are you allowed to go down again? No, you're not allowed. So we can use state, because you're allowed to set state, and that's really smart. So you can use that kind of information. And the last one is we had like a many-to-many problem. Like basically, it's like if you have the user wants to check if you have access to the op department, but the op department has many thousand subscriptions, so that's a valid use case we have. And the IT department has many thousand subscriptions. But the problem is they have two kind of relationships back up to the department node. That's they have a payer role and an owner role. So in order to do this, you might get unlucky. So your traversal actually needs to go down to all the subscriptions to find maybe that one subscription that has a owner relationship pointing to the IT department, which is connected to the user. So worst case, this will be very time consuming, and this applies really to the end-to-end market. So during the analysis, we discussed this problem. So basically, we were lucky we found, like, after reading the secret code one time, where we found that we had a loophole there that we actually was a special access that is applied to, and it only applied if the user had direct access to the subscription. So in reality, we escaped solving this problem. But one thing that is about like context. So it's one way we could have solved this was to add information saying that it's connected to this subscription, and then we add additional information to the query, and then we can escape the time problem. So very fast, the last part is there. So just the deployment model, we have two instances. We don't use the HA solution. At the time when we used it, we went with 1.8. Then we needed to do like zookeeper to have HA. We didn't want to do that. We didn't need to do that. Of course, we don't have master data in EFJ. And also, there is a cost of having the additional model. Okay, the business rule are really simple there, but you have a lot of code just to have the replicated model. So that is a cost. And also the competence is, at least in Norway, not really easy to find. So yeah, we need to think about this. It's easy to find developers who actually can work with this. And we need to do major redesign of some existing use cases, because basically it was based on joint simulation database before. So it is some work to do it. An extra area that we didn't do that we might have done was combining access control list with the graph. So because you need to do the traversal each time. So one thing we could do is, instead of doing the computing at the request, we could react to events instead. So that when something changes in the graph, find the users who are affected, do the calculation and store them in that list instead. That's one way of doing it. And if we did that, we could actually escape the extra logic that we have for like the U-turn and the drop versus flatten out. But we didn't get that far, so yeah. So basically it was worth it, yes. Because we get kick-ass performance, and it makes our solutions very responsive, and the user experience is really great, and that's really important for us. And yeah, final questions? Anything? Yeah?
So how frequent are you moving the data from the RDBMS database to
From the relational database?
Yeah.
Okay, so how often do we replicate data from the relational database into the graph database? So we had that number, I think it was 50,000 a day. So let's see. 40,000 updates, daily updates.
So when you say real-time update, it's every second, every minute?
So it's extension to the relational database we have Sybase, it's add-on product. So basically it's milliseconds. So when there is an update of the relational database, it's instantly put onto a queue, and the queue is read from the service that hosts the EFJ solution. So it's milliseconds. It's basically push one button like insert and it's updated. It's really fast. So the only thing you don't have is it's not within a transaction, but otherwise it's near real time. Yes.
Okay. If you go one slide further, you have the production data at the top. Can you say a little bit about this timing pattern? Because there seem to be very regular spikes in terms of the access time.
Here on top?
Yeah, in the yellow, for example, in the yellow 99 graph.
Okay, I actually have analyzed that. I haven't seen really looked into the pattern, but I know that since we have like the daily load, like total resync of the database as of now, because we're not like 100% sure that everything is working with the message queue. So it might be just during population that we have spike. But I haven't analyzed it any further. Yeah.
So you said it takes 1 millisecond to run through the whole graph for one resource?
It takes 1 millisecond, like with the entire graph, like where you have how many? So we have 27 million nodes there, right? And you have one resource, one user, and to see if you have a valid connection using the rules and everything, takes 1 millisecond.
So when a user logs in, how many resources do you have to evaluate?
When a user logs in, now we don't evaluate any resources. So we just evaluate when he asks for a resource. The first time you ask for a resource, then we do the computation and it takes like if you log on, even doesn't matter how big customer you are, like you have many hundreds of thousands. It takes, you ask for a subscription, it takes 1 millisecond to get response if you have access to that subscription.
Okay, so your access pattern is that the application asks for one resource at a time.
Okay, so if I mean there are different use cases, but the question is if it's always asked for one resource, No, but a lot of, most of the time it asks for one resource, but we have also like search functionality and like open search for all the data you have, see if like you have a match for the word and something. So in that open search, you basically ask for all the resources you have access to, and we actually combine that using like the Solo UC as a search engine. So it's also used in that fashion.
So when, let's say I'm asking for 10,000 resources, I'm searching on 10,000 resources, and I need to know what records I have access to. Are you going to run all the resources through this engine?
So if your question is that if it's searching through all your resources, then we will retrieve all the resources you might have access to and filter this result based on that, yes.
That might take a lot of time, then, I mean, because...
No, it's really fast. So there's a link at the end to the original project, and there, so it's also on SlideShare, like last year in Oslo. And there you'll see like the combination with Solo you've seen and also the response times that you get. So they're really fast also when you retrieval. Because again, if retrieval data is just like 2 seconds, and we also do it like smartly. So, but you can see the other presentation on SlideShare if you want more details about the total solution. Yeah?
How long does the daily restart take?
I'm sorry, can you speak up?
How long does it take to do the daily restart?
The daily population. Okay, so how long time does it take to do the daily population? I think it takes about 45 minutes each night. So what we do is, of course, we have 2 instances. We shut down 1 instance, and we turn off like a queue for that period, so only do the population, and then we switch back on. So it's not downtime at all for users. I'm out of time, so if you have any more questions, I'll be available here for the day and also after tonight, like at the after party or whatever. If you have questions, then come to me. I'm more than happy to answer all your questions. Okay? Okay, that's it.